welcome back. We are about to get into chapter 9, which is our last topic in the semester, which is inferential statistics. So chapter 9 is about one sample test. Chapter 10 is two sample tests. Okay? So if you have good understanding in chapter 9, then chapter 10 is just a piece of cake. Right? So you will enjoy learning about this. Right? So last class in chapter 8, we talked about the confidence interval. Okay? And the confidence interval, we talked about the sampling distribution, which is distribution of sample means. Okay? And the formula for the confidence interval, typically we say 100 times 1 minus alpha percent confidence interval for population mean, which is unknown, right? That was z alpha divided by 2 times sigma over square root of n. And of course, if you don't know the sigma, then you should use t distribution. We learned that, right? And sometimes we use a slightly different standard error if you're dealing with proportion, right? So that was about the confidence interval, right? So sometimes the confidence interval will include some hypothesized value of the mean, right? If somebody says this is the population mean, right? Then let's say this was 95% confidence interval for the mean, right? And if the lower limit and upper limit include, this range includes somebody's claim, right? Then, you have no way to argue it or dispute it, okay? Because the typical interpretation of this confidence interval is you are 95% confident that the actual population mean exists between these two numbers, right? So it is, the person, if someone claims that population mean is exactly a certain number, right? Then that person might be correct, right? Right? But for some reason, your sample mean came out to be pretty far away from this number. So when you calculated the confidence interval, that confidence interval range does not include this number. So this mu0 is outside this confidence interval, right? Then you can say it is highly unlikely, right? Because what you know is with 95% confidence, you can say that actual population mean exists within this range, right? But this range does not include or contain this certain number that someone claims, right? Then you have, pretty good reason to reject that claim, right? So that's the idea of confidence interval or interval estimation, which was the first method of making statistical inference, okay? Well, in chapter 9, we're going to do slightly different thing. We basically the same idea. We're trying to test someone's claim, right? But this time, instead of calculating the confidence interval, we will directly test that claim, okay? So that's the idea of point estimation instead of the interval estimation, okay? All right, so first thing we have to understand is about hypothesis. What is a hypothesis? Right? We're going to talk about two different hypotheses in this chapter. Okay? And first one is called the null hypothesis. Null hypothesis. And we use H naught. You can say H0, or typically we just call it H naught. Okay? Or this is null hypothesis, okay? As opposed to alternative hypothesis. And depending on textbook you use, some textbook use HA for alternative, but our textbook uses H1. So H0 versus H1, or H0 versus H1, right? That's what we're going to use in this class. Okay? So it's just a claim or assertion about a population parameter. You know, there is an unknown population parameter, and somebody claims that the population parameter has certain value, right? And that's what we can call a null hypothesis or a hypothesis. Okay? So these are just a couple of examples. Somebody claims population mean is $42 or population proportion is 0.68, right? Those are examples of hypothesis. Okay? The null hypothesis is always the beginning of the test, okay? Or hypothesis testing. Okay? And then we assume that the null hypothesis is true. We start out with an assumption that the null hypothesis is true. If somebody makes a claim, right? Say H0 says mu is $42, okay? Then we're going to start out the test with the assumption that it is true, right? But then, the whole process is to find the sufficient evidence to reject this null hypothesis. We start out by saying, assuming that it is true, right? And we are trying to find out whether we can find sufficient evidence to reject it. Okay? So that's a very important point. The whole direction of the test is to see whether we can reject the null hypothesis or not. Okay? Remember that, right? And the idea is similar to the notion that, if you watch any TV show, the crime TV show, what is it? The CSI or something like that, right? And you've probably seen many times in the trial, any criminal trial, any suspect is, I guess, presumed innocent until the person is found guilty, right? So it's the role of the prosecutor to suggest or find sufficient evidence to convince the jury, right? And the jury is convinced that there is sufficient evidence, they will find the person guilty, right? But until you find sufficient evidence, the suspect should be presumed to be innocent, okay? So that's the similar idea, right? So the question is whether we can find sufficient evidence to reject the null hypothesis or not. Okay? Typically, null hypothesis contains equal sign or greater than or equal. In other words, mu is at least certain number or less than or equal, right? So at most, okay? So if these signs contain equal sign, right, then that can only go on the null hypothesis. The null hypothesis contains equal sign. Okay? As we go on, you will see what we mean by that. Okay? The most important thing you have to remember here is you should never accept the null hypothesis. Okay? So if you find the sufficient evidence to reject it, then you will reject it. If you don't find sufficient evidence, then you should simply say, do not reject or cannot reject, right? You should never accept it. That's a completely different thing, right? So in a few minutes, I'll give you a more detailed idea about that. And I emphasize this many, many times throughout the chapter, right? But when students take the test, there are a few people who still accept the null hypothesis, right? And you will never get my sympathy in grading. All right? Alternative hypothesis, the second line here, okay, is simply a negation or the opposite of the null hypothesis. It's simply the opposite of the null hypothesis, right? So in this case, if the null hypothesis says mu is equal to 42, the opposite is mu is not equal to $42, Okay? That would be the alternative hypothesis for this null hypothesis. Excuse me? You have to get my permission. Do you have any reason to go out? Somebody's locked out? Huh? Okay. Thank you. All right. So if someone claims that the average number of TV sets in U.S. home is not equal, I guess this is the alternative hypothesis, right? Because it says not equal to, right? The alternative hypothesis can contain not equal to, greater than, or less than, right? It cannot contain equal sign, right? So if the alternative hypothesis was not equal to 3, then you can guess what the null hypothesis was, okay? Any idea? What was the null hypothesis in this case? Right. The null hypothesis must have been the average number of TV sets in U.S. homes is equal to 3, right? So that's just the null hypothesis and alternative hypothesis are just the opposite, right? All right. So the idea of the hypothesis testing is that the researcher is trying to prove the alternative hypothesis is true. In other words, if you are trying to reject the null hypothesis, that means you are trying to prove that alternative is true, right? It is okay to accept the alternative hypothesis, right? But you should never accept the null hypothesis, okay? I'll explain why in a few minutes. Okay? So here's just another example, or actually a little bit more detailed ideas about the hypothesis testing. Okay? Let's say we have a null and alternative hypothesis claiming mu is equal to 50 as opposed to mu is not equal to 50. Okay? So in order to make the decision, we're going to take a sample, okay, and calculate the sample mean. So this was the age question. So someone says population mean age is 50, right? And maybe someone took this class as a sample, right? So if you calculated the average age in this class, you'll probably get something close to 20, right? Which is significantly lower than 50, right? So if you use this class as a sample, then probably the most likely decision is you will say, let's say, so we have null hypothesis says mu is 50, alternative says mu is not 50, okay? And if you use this class as a sample and make the decision based on the sample mean, then probably you will have to reject the null hypothesis because 20 is just too far away from 50, right? So that's the very simple and rough idea about hypothesis testing, right? So we're going to take a sample, or we're going to find an evidence based on some sample, right? And see how close our sample evidence comes to the hypothesized mean, right? And let's say if sample mean came out to be something like 45, right? Then we may not have enough evidence to reject the null hypothesis. Because depending on the sample, I mean, when the actual mean of the entire population is actually 50, right? Depending on how you select a sample, right? Then you might very well get a sample mean of 45, right? Somehow you just selected a few more younger people than average, okay? But if sample mean came out to be 20, right? Then with certain confidence, right? Certain level of confidence, you can easily say this is not true. Our evidence suggests that that's not true, okay? So that's the idea. Graphically, this is what we're talking about. we have a sampling distribution. This is the distribution of X bar here, right? But when we first learned the sampling distribution, we talked about the concept of unbiasedness, right? Unbiasedness means if the population is normal, right, then the sampling distribution will be centered at population mean, right? So if someone claims the mu is equal to 50, let's start out by assuming that's true. Again, remember, we start out by assuming the null hypothesis is true, right, if someone claims, right? So assuming that it's true, how likely is it that our sample result will come out to be this small, right? Apparently 20 is far away from 50, right? So, the probability, let's say this was about 1 standard deviation distance, right? So within 1 standard deviation below and above the mean, we're going to have 68%, right? 2 standard deviation, 95%. If this 20 is right outside, let's say, 3 standard deviation area, right? Or, well, let's say 2 standard deviation, right? So what we're doing here is say, let's assume that population mean was actually 50, right? And let's say sigma was 15, right? Then within 1 standard deviation, which is what, 65 and 35, we're going to find about 68% of the sample means, right? And that means if you take the sample 100 times, then 68 times, your sample mean will be between 35 and 65, right? And if you take the sample 100 times, but 95 times out of 100 times, right? That will be between, 80 and 20, okay? So that 20 is so far away, right? And let's say, to make it simple, sigma was slightly smaller than 15, say 14.8, right? Then this would have been 20.4, right? So the probability that you will get 20 as the sample mean will be even smaller than 5%, right? 2.5%, right? If this was 95%, right? Then you have 2.5% here and 2.5% here, right? So probability that you will get that small number, 20, as the sample mean, if the population mean was actually 50, that's only about 2.5%, right? So it's highly unlikely that you will get that much difference between the sample mean and population mean, right? Then with some confidence, let's say with 95% confidence, you can say this is not true, right? This is not true, okay? So that's the idea, rough idea of hypothesis testing. Is it okay? Does it make sense? Just try to get the overall understanding at this point, right? We'll get to the detail in a few minutes, okay? So the next question you can ask is, okay, now I get the idea. If the sample mean is far away from the hypothesized mean, or if from somebody's claim, then we're going to reject it, right? The question is, how far is far enough, right? You say if it's far enough, then you should reject it, right? But what's the criterion, right? How far is far enough? So in order to understand, we're going to get to the idea of critical values. So just like what we did here, right? Depending on the confidence level that was required for your test, right? We're going to set up certain range, right? Something like this here, right? So I'm going to come up with certain critical value or cutoff value, right? And if the sample evidence comes within these two critical values, then I will not reject the null hypothesis. In other words, I cannot claim that the sample evidence is far enough from the hypothesized value. So we will not reject the null hypothesis. Only when the sample evidence comes out to be outside these critical values, right? Either positively or negatively, right? Then we will reject the null hypothesis because we can now claim that we have sufficient evidence that indicates that population mean is different from 50. Okay, so that's the idea of critical value, and so the area outside the critical values, we have two areas on the on the upper tail and lower tail, right? Those areas are called the rejection region or region of rejection. We simply usually use RR, rejection region. Okay? The area between the two critical values is called the region of non-rejection, right? Or non-rejection region. Okay. All right. So about how to calculate the critical value exactly, we'll get to that in a few minutes, right? But before we get to the actual mechanics of calculating critical value, let's try to understand some very critical, very crucial concepts here. Okay? In hypothesis testing, there can be two different types of errors. Okay? Well, try to understand this table. On the first row here, we have actual situation. In other words, this is the true state of nature, what is actually true in reality, right? We call it actual situation, right? In actual situation, either null hypothesis is true or false. Again, we don't know population mean, right? But either this one is true or false, right? There cannot be any other case. If someone claims this population mean is 50, that can be in actuality, right? In reality, it can be true or false, right? And then the researcher, the person who run the test, right, can make two decisions. Either the person can accept the null hypothesis, reject the null hypothesis. I told you never accept the null hypothesis, right? So this is the reason why, right? So if the person didn't know that the person should not accept the null hypothesis, then in typical situation, in the normal situation, depending on whether the person finds sufficient evidence or not, you would be inclined to accept the null hypothesis or reject the null hypothesis, right? If null hypothesis is really true and the null hypothesis was accepted, then that would be a correct decision, right? If in reality null hypothesis was false, then rejecting it would be the correct decision, right? Well, if the null hypothesis was true and for some reason the researcher rejected that null hypothesis, there would be an error, right? And we call it type 1 error. So type 1 error is an error of rejecting the null hypothesis, which is actually true, right? That's the type 1 error. Okay? There's the other type of error, which is when the null hypothesis is actually false, the researcher mistakenly accepted, right? That's what we call type 2 error. Okay? All right. So here's the definition of type 1 error and type 2 error, rejecting the null hypothesis when it is in fact true. Okay. And we call the probability of type 1 error alpha. probability of type 1 error. We call it alpha. Okay? And that's exactly the same alpha as I introduced last week or last class, right? Level of significance. Level of significance, that's the formal name of alpha, level of significance. But that's actually the probability of type 1 error. And this error, this probability is set by the researcher in advance, depending on the level of confidence you require, right? Remember, level of confidence or confidence level is 1 minus alpha. Okay? So if for whatever the purpose may be, your conclusion requires, say, 95% confidence, right? You want to be 95% confident about your conclusion, right? Then your alpha level would be 0.05, right? In other words, you're setting the probability of committing type 1 error in your conclusion to be 5%. In other words, you are saying you are willing to accept the probability of type 1 error up to 5% of the times. That's okay, right? Why? Why do we have to accept the probability of error? In other words, is there any way we can completely eliminate chance of error? Is there any way you can be 100% accurate in your conclusion? There's only one way. What's the way? Any idea?
The collection of sample is the whole.
Entire population, right. If you use entire population, right, to make your conclusion, then there will be no doubt, right? If you have, say, 1,000 people in your population, right, or 1 million people in your population, and collect all their ages and calculate the mean, there is absolutely no error, right? You can be 100% confident, right? But as long as you use a sample, then there is no way you can be 100% confident, right? So that's why we set up this level, alpha, right? You can control the amount of error you can commit, right? But there is no way you can eliminate unless you use entire population. If you use the entire population, then you don't need any inference. You don't need to learn this hypothesis testing, right? Why would you bother, right? You know it for certainty, right? So that's the idea, right? All right, the important thing is you can control it. You set it before you start the testing, and you make the conclusion based on your level of significance, okay? For example, I don't like that color, right? In the example before, we start out by assuming that population mean is actually 50, right? And the sigma was, say, 14.8, right? So 2 standard deviation came out to be, 20.4, something like that, right? Right? But our test statistic indicates that the sample mean indicates that it is 20, right? Then I told you that you can probably reject the null hypothesis because that chance is only 2.5%, right? But still, it is possible that this is true. Somehow, you select a bad sample like this, right? Somebody asked you to come up with the population mean in the entire South Korea, right? And you use this class as a sample, right? So that's a very bad sampling, right? That's not very representative, right? I mean, the first-year college student cannot represent the entire population, right? So if someone decides to use this class as a sample for the entire population, that's a mistake, right? But somehow it can happen, right? So it is highly unlikely that still it is possible, even when the sample mean came out to be 20, right? This null hypothesis could be true. You cannot eliminate that possibility completely, right? So that's the idea, right? But because it's so unlikely, and there is no way you can eliminate the probability of error completely, you may decide to use 5% chance for type 1 error. In other words, you set up 0.025 area on the lower tail and another 0.025 area on the upper tail, and say whenever my sample result indicates here or here, then I'm going to reject the null hypothesis. Right? That's the idea, right? So if your sample result indicates here, right, rejection comes out within the rejection region, then there are two possibilities. First possibility is null hypothesis is not true, or null hypothesis is false. That's the first possibility, right? Because your sample result is so far away from what the null hypothesis claims, right? Second possibility is null hypothesis is still true, but a very rare event has occurred. A very rare event has occurred. Okay? So somehow when you selected a sample from the population, only very young people got into this sample. Right? If you were a good sampler, right, then you wouldn't make that mistake. Right? That's a bad mistake. You are using non-representative sample, right? But somehow it's still possible. I mean, even if you did not intend to use this class or college class as a sample, it could happen. I mean, if you just selected, 40 people on the street, right? Somehow at that time, only the young people were on the street, right? Maybe there was some event for young people around that area, right? So it is still possible. But the probability or chance for that event is very small, right? So what we're going to do is we're going to ignore this possibility because it's highly unlikely. This is more likely, a lot more likely, right? So we're going to say null hypothesis is false, right? That's the idea, right? Type 1 error, right? So what I'm saying here, in consequence, is this area plus this area, that's exactly alpha. So on one side we have alpha divided by 2, alpha divided by 2. Right? That's exactly as we've done before. Right? How about type 2 error? Type 2 error is error of accepting the null hypothesis when it is in fact false. That could happen, you know. I mean, according to this table, there are only two possible errors, if not this one and this one, right? It is possible that you can accept it mistakenly when it is in fact false, right? The size of probability for type 2 error is called the beta, right? But the beta depends on the alpha value and the sample size. There is a trade-off between alpha and beta, right? If you try to minimize alpha, probability of type 1 error, then you end up allowing more probability for type 2 error, right? And it also depends on sample size. Okay? The more exact discussion of beta requires a little more advanced discussion, right? So in this course, we're not going to worry about it. Okay? So instead of trying to deal with beta or probability of type 2 error, we're going to avoid committing type 2 error by not accepting it. Try to understand what I'm saying, right? The type 2 error is error of accepting the null hypothesis when it is in fact false, right? So as long as you don't accept it, you're not going to commit type 2 error, okay? So if you cannot reject it, if you cannot reject the null hypothesis, then you simply say do not reject or cannot reject. Just never accept it, right? That way we will try to avoid type 2 error. Okay? See if you can understand that, if you have any question. As you gain your understanding, that you will see that this is simply play of words. Okay? It's really, it doesn't make any sense, right? Avoiding type 2 error by not accepting it. Let's say in realistic situation, suppose you are producing certain machine components, right? And let's say O-ring, right? I guess you guys never heard of this O-ring, right? O-ring, usually the ring that seals the gas or liquid from leaking from a container, right? So when I guess in a bottle, in certain thermal bottle, right, you may find some O-ring, right? So let's say you produce O-ring and the exact specification requires, say, 2 centimeters, right? If it's too small, it's going to leak. It's going to leak the liquid or gas, right? If it's too big, then it's not going to fit, right? So it requires exactly 2 centimeters, right? So the quality control people will try to sample your products every hour, right? And try to find out the average size, right? Even if you have very good, precise machine, right? In reality, there may be some variation, right? So it's sometimes 2.001 centimeter or 1.999 centimeter, whatever. But there may be some slight variation, right? And there may be some range of variation that may be acceptable, right? Anyway, so the null hypothesis claims that the population mean is 2 centimeters. Alternative hypothesis says population mean is not 2 centimeters, right? So quality control people will run this test after sampling, right? And if they can reject it, if the conclusion says reject the null hypothesis, then what are you going to do? Suppose you are the quality control guy, right? You are production manager, right? You found out based on the batch of sample you just produced, you end up rejecting this null hypothesis. What does that mean? What should you have to do? Do you understand the example? The story I'm telling you, right? So if you're the production manager and your quality control people say, hey, we took some sample and measured and ran this test, right? And we rejected the null hypothesis. What is your action? What should you do? What does that mean in production setting? Are you okay? Huh? Can you continue the production? No, because apparently you have sufficient evidence that the average size of the parts that you're producing is not 2 centimeters. Either it's too big or too small, right? So the conclusion is your machine is malfunctioning, right? Something's wrong, right? So what should you do in that case? What's the course of action that you should take? Before you fire people, right? You should shut down the machine and adjust it, make some adjustment, right? Investigate what's wrong and make some necessary adjustment before you continue the production, right? Well, of course, if this happens every day, then you should fire some people, make some changes, right? Right. Well, what if you cannot reject? Suppose after the result, after the test, right? Your conclusion was do not reject the null hypothesis. What do you do? You have to continue the production, right? But does that mean that your machine is perfectly fine? Does that mean, if you say machine is fine, so we're going to continue the production, that means you are accepting the null hypothesis, okay? So rejecting and not rejecting and accepting are two different things, right? Not rejecting means you have insufficient evidence to reject it, right? So you have insufficient evidence to say machine is malfunctioning or beyond a certain limit, and we got a problem. You cannot say that. You don't have sufficient evidence, right? But that's a totally different thing from saying machine is perfectly fine. And the population mean is exactly 2 centimeters. Okay? So in theory, on paper, there's a difference, right? You can say we cannot reject it, right? But in reality, if you do not reject, what is your course of action? You have to continue. Because you have only two choices. You either shut down and adjust, or you continue, right? In reality, there is no difference between accepting and not rejecting, right? But in theory, on paper, especially when you take an exam, right? You should never say accept it, right? Because if you accept it, there is a probability or chance of type 2 error, okay? And probability of type 2 error is beta. And we have we have not done anything about beta. We are not controlling beta, right? About alpha, we have set the limit, right? If you say alpha is 0.05 and make the decision based on this, right? So only when our test statistic comes out to be way outside within alpha divided by 2 and alpha divided by 2 area, right? You decided to reject it. So you are controlling the chance of type 1 error, right? About type 2 error, we haven't done anything. So if you decide to accept it, right, then you have no idea what kind of risk you are taking. Okay? That's why we say do not accept the null hypothesis, okay? And just simply say do not reject. If you cannot reject it, instead of accepting it, right, just say do not reject, right? But in reality, there is no difference. If you do not reject, you have to go on, right? So if you want more, I'm sure you have some question about that. Can we do a little more than that? Yes, but you have to take a little more higher level theoretical statistics class if you want to analyze about beta. Okay, don't worry about beta in this class. Okay, it's business statistics. Okay, so here's a little more realistic example. So, based on what we've talked about so far, right? So here, null hypothesis claims that mu is 3. Alternative claims mu is not 3. And let's say level of significance is alpha. Then we're going to set aside the rejection region on each tail, right? Depending on the alpha. So I guess you have the idea now, right? Because because we are setting aside alpha divided by 2 and alpha divided by 2 on each side, right? The next step is we have to find the z-score, which has alpha divided by 2 on its outside. Z-score alpha divided by 2. So if this is z alpha divided by 2, this is negative z alpha divided by 2 because it's symmetric, right? And you know how to find out, from the z table, right? If this happens to be 0.025, that's the z-score, which has 0.975 on its left side, okay? So you find out that z-score, right? That's going to be the critical value. All right. And, okay. With this, the slide says at the bottom that this is a two-tailed test because there is a rejection region in both tails. We'll talk about that later. Later, more exactly, we'll talk about the difference between two-tailed test and one-tailed test. Okay. All right. Well, maybe. But the only difference is, okay, let me explain it now, right? So sometimes researcher wants to know mu is exactly 3 or not. So all you want to know is the population mean is exactly a certain number or not, right? Exactly equal to that number or different from that number. Sometimes researcher wants to know mu is greater than 3 or at least 3. Okay? So if the alternative, remember, equal sign cannot go on alternative hypothesis, right? So alternative hypothesis claims at least 3, right? Then the null hypothesis should say less than or equal to 3. Okay? Something like miles per gallon, or in Korea, I guess it's kilometers per liter, KPL, right? So when you buy a car, right? If you want to find out how fuel efficient this car is, with 1 liter of fuel, right? How many kilometers the car can go. I think the new Kia model claims that it's something like 13. Is that about the right number? 13 kilometers per liter. Is that good fuel economy? All right. So if the car company claims that you can go 13 kilometers with 1 liter of fuel, right? Then you want to test. Is that true, right? So on average, really, is it greater than 13 or less than or equal to 13? Okay, right? So, or depending on the setup, right? If in this case, the company claims that mu is at least 13, right? And that means your researcher, the job of researcher is to prove that it is less than 13, right? So if you have sufficient evidence for this, then you will be able to reject this claim, okay? So depending on the context of the problem, you should be able to set up the null and alternative hypothesis, okay? So these are what we call one-tailed test, right? Because in this case, all you need to find out is whether your test statistic exceeds critical value or not, right? You don't have to worry about left side or lower tail, okay? Because the question is whether it is greater than or not greater than, right? In this case, that will be opposite, right? In this case, your rejection region will be only on the left side, right? Because we want to find out whether the critical value, the test statistic is less than or not less than critical value. Okay? So these are one-tail test. This is a two-tail. Okay? The difference is if you want to be 95% confident, right? If you want to be 95% confident in your conclusion in two-tail test, then you have to distribute half of 0.05 on each side, right? But if you're running one-tail test, you can set aside the entire 5% area on one side, okay? Entire 5% area on one side, okay? And in making the decision, you can use that rejection region, right? So that's the difference between two-tail test and one-tail test. All right, so here's exactly how we come up with the critical value, okay? Critical value Z, if the sigma is known, okay, then we can use Z statistic as the test statistic, the test statistic, right? Not critical value, sorry. The test statistic Z is X minus mu, the sample mean minus hypothesized mean, divided by sigma over square root of n. Okay? In other words, we are converting, and so far today's class I used this example, X bar, say somebody claims mu is 50 and our sample mean came out to be 20, right? So I told you that because that distance is significant, right, we could probably be able to reject the null hypothesis, right? In reality, we have to do one more step, right? In order to make the conclusion, we have to convert this X bar into Z scale, right? And convert the actual distance here, let's say actual distance is 30, right? That into Z-score, how far this 20 is from 50, considering the standard deviation. That way we can compare this critical value. So critical value is X bar minus mu over sigma over square root of n, right? We are converting this actual distance into Z-score by dividing with the standard error, right? And that way we can compare the test statistic with our critical value Z-score. Told you the critical value is a Z over alpha divided by 2 in two-tailed test, right? So if somehow this Z-score, the test statistic, this is test statistic. If this test statistic comes out to be greater than or less than the critical values, right, which are Z-scores, right, then we should be able to reject the null hypothesis, right? So that's why we are converting this actual distance into Z-score, right, and make it a test statistic, right? All right, so test statistic is Z if the sigma is known, right? If sigma is unknown, well, we'll talk about it in a few minutes later, right? But you know what the answer is, you know. Instead of sigma, you use S, right? Then instead of Z-score, you have to use T-score, okay? That's the only difference, okay? Okay, so here's a kind of, summary of what should actually happen. Critical value to testing. Critical value approach to testing, right? Let's say sigma is known and you are running two-tailed tests for the mean, right? Then convert the sample statistic, sample mean, to the test statistic Z to make it test statistic, right? And then determine the critical value Z, which has alpha divided by 2 area on its outside. So from the z table, you can find the z-scores, which has alpha divided by 2 on its outside. Those are critical values, right? Critical values. And compare the test statistic and critical value and make a decision. If the test statistic is outside, either positively or negatively, so this is negative test statistic, or it could be test statistic, right? In other words, at this time, if you convert it, it's going to be 20 minus 50, say, divided by 14.8, right? That's going to be something like negative 2 point something, right? So in that case, test statistic will be negative on this side, right? But somehow your sample mean was 70 instead of 20, right? Then your test statistic would be 14.8, would be something like 1 point something, right? So that in that case, the test statistic would be on the positive side, okay? So decision rule is if the test statistic falls in the rejection region, reject the null hypothesis. Otherwise, do not reject the null hypothesis. Again, never accept the null hypothesis because we haven't done anything about the type 2 error. Type 2 error is not controlled, okay? That's it. That's the simple idea of hypothesis testing. And here again, the summary review of the steps in hypothesis testing. You start out with a null hypothesis and alternative hypothesis, okay? And you have to decide your alpha level. What is it? The name is level of significance, but what's the concept of alpha? It is probability of which error? Type 1 error, right? Remember, alpha is the probability of type 1 error. What's the type 1 error? It's the error of rejecting, right? Excuse me. Remember, this area is alpha, or alpha divided by 2. And whenever you find test statistic in this area, you're going to reject it, right? So either you are correct in rejecting it or you are making an error by rejecting it, right? So that's type 1 error. Type 1 error is possible. That's the error of rejecting null hypothesis when in fact it is true, okay? When in fact the null hypothesis is true, right? All right? So the next step is based on your sample statistic, you have to calculate the test statistic. Again, test statistic is conversion into the standard normal value, z-score, right, of the distance between the sample mean and population mean, right? So make sure you get this clear, intuitive understanding. From the beginning of this class, I told you that what matters is the difference between somebody's claim in the population mean and your sample result, right? If this is too large, if it's too far away, right, then you have sufficient evidence to reject it, right? So simply, you are comparing that distance to standard error. Standard error, right? So if it comes out to be 2, that means this distance is twice as large as standard error of the sampling distribution. Remember, standard error is a standard deviation of the sampling distribution, okay? So compared to what, can happen, compared to the variability, we're talking about sampling distribution here, distribution of sample means, right? And the standard deviation, so sigma over square root of n, right? That's the standard deviation among the sample means, right? So this is a measure of variability among the sample means, right? You know, standard deviation is a variability of random variable, right? If standard deviation is a variable, it measures the spread or variability of any random variable, right? Standard error, that's the standard deviation of sample means, right? That's the measure of variability among the sample means, right? But what makes that variability? In other words, what causes that variability among the sample means? Population mean? We have only one population, right? And there can be only one population mean, right? But we can have multiple samples, right? So we can have multiple sample means, right? We have a distribution of sample means, right? So the story is we have one population and one population mean, which we don't know, right? But depending on how you select a sample, every time you select a sample, we may get slightly different sample means, right? So we're talking about this variation among the sample means. That's what we call sampling error, right? This variation is there because our sampling technique is not perfect. If sampling technique was perfect, in other words, every time you selected a sample, the sample perfectly represented the population, then all the sample mean would be the same, right? But because we are selecting random sample, right, we have this variation among the sample means, right? And that variation is measured by this standard error, okay? So you can say, this is a measurement of sampling error. So compared to the sampling error, typical variation we have when we do the sampling, right? How far is our sample mean from the population mean? We're comparing that to the typical error or typical variation, right? And if that is significantly large, then we can say, well, even when we consider this typical variation that can come from the sampling error, right? This distance is just too far away, right? And that means the null hypothesis, if someone claims, right, say mu is equal to a certain number, right? Probably this is not true because our sample result is too far away, too different from somebody's claim. Okay? Even when we consider the regular, typical, usual variation. Okay? That's the whole idea of the test statistic and also the idea of hypothesis testing. Okay? So determine the critical value that find the rejection and non-rejection regions and compute the test statistic. If the test statistic is outside the critical value, either positively or negatively, right? And that means we have sufficient variation or deviation of our sample result from somebody's claim, right? And we can reject the claim, right? Null hypothesis, right? If not, you simply say we cannot reject the null hypothesis. That means there is insufficient evidence for that to refute or reject that claim. Okay? So here's an example, right? Let's say someone claims that the population average or mean number of TB sets in U.S. home is equal to 3, and let's say the sigma somehow is known, population mean is known, standard deviation was known, right? Then the null hypothesis says mu is equal to 3. Alternative says mu is not equal to 3. So all you want to know is whether it's 3 or not. You don't want to find out whether it's greater than or less than. That's not your interest. Okay? In that case, you will run two-tailed test, right? And you have to decide alpha level. Suppose you decided alpha to be 0.05, which means you want a 95% confidence in your conclusion, right? And you decide to choose sample of 100 observations, okay? Then, because sigma is known, we're going to use z-test, right? And test statistic, so sample mean came out to be 2.84, right? So when you convert that into test statistic, you come up with negative 2.0, right? And that means this distance between x bar and mu is 2 times the standard error, right? All right? So you look for the critical value. What's the z-score which has 0.025 on its outside? We find out it's 1.96, right? So we have this critical value here, 1.96, and negative 1.96 as critical values. So the area between the two critical values, the rejection for not reject, the area for not rejecting, right? And those area outside the critical values are rejection region, okay? And this time our test statistic is negative 2.0, which is here, which is outside negative 1.96 or inside the rejection region, right? So the conclusion is reject the null hypothesis and say there is sufficient evidence that the mean number of TVs in U.S. homes is not equal to 3. Okay? So just saying reject the null hypothesis is not enough. You have to also make the interpretation. What does that mean in the context of the problem, right? Make sure you do that. Any question? But, we already talked about in the previous chapter that assumption is probably very unrealistic, right? Population standard deviation sigma is known, right? So what if the population standard deviation sigma is unknown? Well, we already talked about this. We can use t-distribution and t-test instead of z-test, right? So here, there are a few things you have to understand, okay? We can use the sample standard deviation S for sigma, right, if the sigma is unknown. But then, because of this change, we have to use t-distribution instead of z-distribution, right? Remember, t-distribution is a little bit wider, which means that we allow a little more variation, right? And it also depends on degrees of freedom, the sample size, basically, right? And when using the t-distribution, we must assume that population you are sampling from follows a normal distribution, right? So what if you cannot easily assume that, right? Then you can say, you can apply CLT. What is CLT? Central limit theorem, right? Central limit theorem can be applied if you are using relatively large sample, which is, the sample size is greater than 30, right? If not, okay, then you can test, see if population can be considered reasonably normal. How do you do that? You can use some tests like a normal probability plot, normal probability plot. That's the way we've used in our previous chapters, right? Okay. So that's one thing you can do, right? If this test, normal probability plot, turns out that you cannot assume that population is normal, then you have to use some other method. Use non-parametric test. Non-parametric test, right? We're talking about entirely different tests. You cannot use z-test or t-test, right? So you can go through many steps here. Right? If you have sufficiently large sample based on CRT, you can assume that population is normal. Well, not population is normal, but the sampling distribution is normal anyway, right? If not, then you can do some tests to see actually whether the population looks like normal, right? If that doesn't turn out to be true, then you have to give up the t-test or z-test, right? And you have to use non-parametric test. Non-parametric test means it doesn't require any specific distribution, right? We're not going to talk about non-parametric test in this course, but if you like, you can read chapter 12 of our textbook, right? They talk about a few different non-parametric tests. Okay? Well, the good news is this. T-test is robust. In statistics, robust means this, right? Test result are still valid even when population is slightly non-normal. Even when the population is slightly non-normal. Okay? That's what we mean by t-test is robust. Okay? So what that means is, when you did this the normality test on the population, it didn't come out to be really straight line, right? A little, skewed and so on, right? Then typically t-tests are still usable. So if you look at actual research in real life, right? Most of the researchers use t-test, okay? Because t-test is still very robust, okay? All right, so having that in mind, let's talk about some examples here. Okay? So here, we're talking about case where the population standard deviation is unknown. Okay, population standard deviation is unknown, so we're going to use the sample standard deviation instead of sigma, right? So that means we're going to run the t-test, right? Well, another problem here is we got the sample size of 25, which is less than 30, right? So this requires an assumption that the population distribution is normal. Keep that in mind, okay? All right? So we have the null and alternative hypothesis. Null hypothesis says, so the story is somebody claims that the average hotel cost in New York City is $168 per night, right? And we want to test this claim, right? So the null is mu is equal to 168. Alternative says mu is not equal to 168. It's a two-tailed test. Excuse me. And we are given to use alpha level of 0.05. So sample size is 25. Degrees of freedom is 24, right? So the test statistic you can calculate this way, right? Using the same formula. Came out to be 1.46, right? And then we have to set up the rejection region, right? In other words, we have to find the critical value, right? So critical value of t statistic, which has 0.05 on its 0.025 on its outside, with the degrees of freedom of 24. We go to t table. Okay, so we look for upper tail area of 0.025 here, right? We have 0.025 here, and then come down to degrees of freedom of 24, which is 2.0639. Is that right? You can use t-table, right? So look for the alpha area, upper tail area, and then come down to degrees of freedom 0.025, 24. So 2.0639, that's the critical value. Right, so that's how they found out 2.0639 here, right? So our test statistic is 1.46, and here, right? So again here, when you run the t-test, I want you to state the decision rule, right? The null hypothesis, alternative hypothesis, test statistic, and the decision rule would be reject the null hypothesis if the test statistic is greater than t of alpha divided by 2. So here, alpha divided by 2 is 0.025 with the degrees of freedom 24, which is 0639, right? Or if the test statistic was less than negative t of 0.02524, which is negative 2.0639, right? Make sure you write down this decision rule, okay? And then after that, you can make your conclusion. What is your conclusion? In this case, does the test statistic satisfy this condition? Either of these conditions? No, right? Because test statistic is only 1.46, right? So it's not greater than 2.0639, and it's not less than negative 2.0639, right? So what is your conclusion? Accept it? No. Do not reject the null hypothesis. And interpretation? Right. There is insufficient evidence to reject the claim that the average hotel bill is $168. Okay? There is insufficient evidence to reject the claim that average hotel bill is $168. Okay? Make sure you say that. Yeah. All right. Now, before we move on to the one-tail test, yeah, we can talk about the p-value approach. This was the conventional approach or critical value approach, right? But what if we want to use p-value approach, right? P-value approach, in order to, again, the decision rule would be reject the null hypothesis if p is less than alpha, right? Simple as that, right? So you have to use, you have to find the p-value, right? But what about the p-value? We have 1.46 as a test statistic. So we have to find the area outside the test statistic, right? But if you look at the t-table, it's kind of hard to do that, okay? Because t-table and z-table are different. If we were using z-table, right, then let's say 1.46 was here, 1.46 here. So we're 1.46, right? So this area outside the 1.46 would be 0.9, well, to the left, right? So actually, it's better to use first table, right? 1.46. Okay, so 0.0721, right? 0.0721. So we can find the p-value from the z-table, right? But we're using t-score, right? And t-table is completely different. These are not the area, right? These are actually t-scores, right? Area is only found here, up on here, right? Unfortunately, we were given just a few alpha areas, like 0.0, 0.25, 0.1, 0.05, 0.025, and so on, right? So with the t-score 1.46, what is 1.46? 1.32, 1.72, 1.4, here's 1.43, 1.47, but with the degrees of freedom, it was 24, right? It's very difficult to find the p-value, right? Actual area outside the t-score, right? So in reality, when you run the test on the computer calculates the area outside. So as soon as computer calculates the test statistic, comes out to be that the test statistic t is 1.46, right? Computer calculates this area and gives you the area, right? Actually, the addition of both areas, this is half of p and half of p, right? So it calculates this area and multiply by 2 and give you the p-value, right? So you can use the p. Once the computer gives you the p-value, all you need to do is just compare that to your alpha level, because you know alpha level. It's in your mind. That's what you set up, right? 0.05 or 0.01 or whatever, right? And you can make the decision right away. So, well, let me show you how to do that. I think you need this for your homework problems also, right? So here, here, you need to use two functions, TINV, T inverse function, and TDIST, TDIST function, right? So this is used to find the t-score, right? In other words, if you were using conventional approach, right, and you have your alpha level, but you want to find the critical value, right? So like here, you want to find 0.025, the critical value which has 0.025 when it's outside, right? Then what you can do is use this command, right? So give the alpha level first, and then degrees of freedom, right? So here I gave 0.05, 300, right? Well, if you want, you can try here. What was the, we have degrees of freedom of 24, and we are looking for 0.025 area outside. Okay, so for example, you can say TINV 0.025, comma, and 24. Yeah, 2.0309. Is that the same thing? Or is it different? 2.0309, 0.025. What did I do here? Let me see if this will make the difference. Yeah, okay, right. Okay, so it assumes the two-tailed test, right? So if you have alpha level 0.05, right? This is a 0.05, so you give 0.05 with the degrees of freedom 24. It gives you the critical value for two-tailed test, okay? Okay. Or if you're looking for p-value, then you can look into your test statistic, right? So here, for example, our test statistic was 1.46, right? And we are running two-tailed test. So what you can do here is equals t distribution, TDIST, okay? And test statistic was 1.46, 1.46, comma, degrees of freedom 24, comma, we are running two-tail test, right? All right. So the p-value comes out to be 0.157. All right. Right. So in this case, what would be the conclusion? The p-value comes out to be 0.157. We are using alpha value 0.05. What is your conclusion? Does this satisfy this rule? No, right? So your conclusion should be do not reject the null hypothesis. Okay? All right, so using the p-value approach is a lot easier when you use the computer to run the test, okay? Because you don't have to look for the critical value. You don't need to use a z table or t table, right? Once the computer calculates the test statistic, it also gives you the p-value, and all you need to do is you compare the p-value to your alpha level, which you are using, right? And you can make the conclusion right away, right? You don't have to worry about all the tables, okay? Okay. T or z of alpha divided by 2. So this is alpha divided by 2 area on each side, okay? And here's negative t of alpha divided by 2, okay? If the test statistic, excuse me, test statistic falls in either here or here, in both cases, you will reject the null hypothesis, okay? Because your sample result indicates that this is just not possible or likely, right? It's highly unlikely. So that was the case of two-tailed test, okay? Well, we just want to talk about the one-tailed test before we finish this chapter, okay? So sometimes you want to, your question is only on one direction. Either you don't care about the other direction, or you are pretty confident that there is absolutely no chance that it will go the other way, right? So for example, in this example, the null hypothesis claims population mean is at least 3, either greater than or equal to 3. And then you want to set up the alternative hypothesis, which claims population mean is less than 3, right? So in this case, the question is, do we have sufficient evidence to reject this null hypothesis, right? If you do, that means you can accept the alternative hypothesis. Again, let me repeat it, right? If you have sufficient evidence to reject the null hypothesis, right, then that means you can accept the alternative hypothesis. It's okay to accept the alternative hypothesis. I told you never to accept the null hypothesis, right? Because there is a chance of type 2 error in case you accept the null hypothesis. But if you have sufficient evidence to reject the null hypothesis, then that's the same thing as you can accept the alternative hypothesis, right? Well, in this case, this is called the upper tail test, because your alternative hypothesis, this is lower tail test, because the alternative hypothesis claims this population mean is less than certain number, right? And if you convert that into t-score or z-score in this distribution, that means your test statistic, you're setting up your rejection region on this side only, okay? Because the test statistic will be something like x bar minus mu 0 over s over square root of n, right? So if the test statistic comes out to be 3 minus 3 in this example, then you're claiming t is less than 0, something like that, right? So you will be focusing on this side only, right? So you will set aside the rejection region only on the lower tail, right? And see if the test statistic falls within this rejection region or not, right? Well, in that case, you don't have to divide alpha by 2 because you are pretty confident that if the test statistic falls in the rejection region, it will happen on this side, right? Or if it happens on this side, you don't care, right? It's okay that the test statistic, well, so in this example, you're saying in one-tailed test, okay, a little bit of hurry here, I guess, today. Okay. Alternative hypothesis claims that mu is less than 3, right? So what you're saying is, all I want to know is whether this is true or not, right? If it's greater than 3, that's fine, right? Or, as long as it is not less than 3, right? So what you're going to do is you're going to set up the entire alpha area. Remember, alpha is the probability of type 1 error, okay? And you remember the concept of type 1 error. What is type 1 error? It's an error of rejecting null hypothesis when in fact it is true, right? So what you're saying is, okay, if this thing happens, I'm going to reject the null hypothesis, right? But, there is still a chance, right? But I'm going to see this amount of risk, right? Probability of type 1 error, I want it to be, say, 0.01 or 0.05, depending on your confidence level, right? And with that much risk, I will still reject the null hypothesis and say this is true, okay? All right, so that's the idea of one-tailed test. So either you can run a lower tail test or upper tail test, okay? Sometimes it's confusing how to set up the null and alternative hypothesis. Let me try to give you a few examples. I think I used this example before. How about the fuel economy? Hyundai Avante, it's called with the name Elantra in the United States, okay? And when I saw their commercial advertisement, they claim MPG, miles per gallon, is 40 miles per gallon. It's hard to convert it into kilometer per liter, because 1 mile is 1.65 kilometers. 1 gallon is about 3.75 liters. So you have to do some calculation. Anyway, okay. So, and I heard a few months ago, this was rejected by the U.S. Department of Transportation. They found the evidence that this is exaggerated. Okay? It doesn't really run 40 miles per gallon. Okay? So in order to test this claim, null hypothesis would have been what? Can you set up the test hypothesis to test this claim? Mu what? Huh? Equals 40 versus not equals 40? You think so? If you are the tester at the U.S. Department of Transportation, right, what do you want to find? If it's greater than 40, does it matter? You don't care whether it's 40 or greater than 40, right? Because what you want to know is whether it's actually less than 40 or not, right? If you want to claim Hyundai is exaggerating, right? So, what do you think? remember, equal sign always goes on the null hypothesis only, right? You cannot have equal sign on the alternative, right? So you want to find out whether it's greater than or equal to 40 versus less than 40, right? Okay? So in that case, you should set it up this way. Somebody's claim is greater than or equal to 40. It runs at least 40 miles per gallon, right? And you want to set up it's less than 40, right? And you want to find out whether there is sufficient evidence to reject this null hypothesis, okay? If you reject it, that means you are accepting this alternative, right? And you can say that claim is false, okay? So in the lower tail test case, something like this, you're going to set up the entire alpha area on the lower tail as a rejection area, right? And if the test statistic falls in this area, you will reject it, right? If it happens to be the upper tail test, then it's the opposite, right? So here's an example. Phone industry manager thinks that the customer monthly cell phone bills have increased and now averages over $52 per month. So you want to claim this, test this claim, right? Well, so somebody claims it's greater than 52, right? So you have to test that claim as opposed against this null hypothesis, okay? All right. So in this case, we want to find out whether there is any sufficient evidence to support the manager's claim, right? All right. So the first of all, critical value to set up the rejection region is you have to. The question says you want to use alpha level of 0.1, right? And in this case, the degrees of freedom is 25, right? So from the T table, where can be the T table? Okay. All right, go to the T table. If n is 25, then the degrees of freedom would be 24 for the T distribution. Okay. And we want to use 0.1 as alpha level. So if you come down here, the critical value would be 1.317, is that 8? Somehow 8 is upside down, right? Okay, so that's how we found 1.318 as the critical value. So we have the rejection region here, okay? And then the next step is calculating the test statistic using the sample mean of 53.1 and the sample standard deviation of 10. The test statistic comes out to be 0.55, right? So do we reject the null hypothesis or not? No, because the test statistic is not within the rejection region, right? So what that means is, when you calculate this test statistic, you subtracted 52 from 53.1, right? And considering the sample variance, in other words, the standard error of the estimate here, this difference, the deviation, is not big enough, right? That was only about half of this usual variation, right? So you cannot say this sample result is really far away or significantly greater than what the null hypothesis claims, right? Remember, null hypothesis claims it is equal to or greater than 52. Less than 52, less than or equal to 52, right? And alternative hypothesis claims it is greater than 52, right? So what we find out is since this difference, our sample mean, is not significantly greater than what's claimed in null hypothesis, we cannot reject the null hypothesis, right? That's the idea. Okay? Any questions so far? All right. Let me briefly stop here.